In this tutorial, we will see how to perform break-even analysis. Break-even analysis is also known as cost-volume analysis. There are really two types of break-even analysis. The first is a single product break-even analysis. Here we look at the cost and revenue for a single product and find the volume where the production breaks even. If that value were 500, then sales below 500 result in a loss, while sales above 500 result in a profit. The second is looking at two ways to produce a product and finding the range over which each is cheaper. For example, if the costs are the same at 500 units, then method A might be cheaper below 500 units and method B above 500 units. Technically, this point is known as an indifference point rather than a break-even point. When looking at production methods, a couple of notes are in order. First, revenue does not matter. More specifically, we assume that the product will sell for the same price regardless of how it is produced. Second, while we will begin the analysis by looking at two production methods, this technique could easily handle more than two. In this tutorial, we will look at both two production methods and three production methods. From that, you will see how the analysis can be expanded to even more production methods. Finally, when looking at two production methods, there's almost always a range where each is the cheapest. However, when expanding the analysis to three or more methods, this is no longer the case. We will look at a single product break-even analysis first. Before doing the math, we can look at the problem visually. In this example, fixed costs are $1,000 and are shown as the blue line on the chart. Since the costs are fixed, they do not change with production volume. Variable costs are $25 per unit and are shown as the orange line on the chart. Since these are per unit cost, as the number of units goes up, the variable costs go up as well. Revenue is $140 per unit and are shown as a gray line on the chart. Revenue is also per unit, so as the number of units goes up, the revenue goes up as well. On this chart, I have combined the fixed cost and variable cost, so the blue line starts at $1,000 fixed cost level with no units produced, and the slope of the line equals the $25 per unit variable cost. The gray line is the revenue and has not been changed from the prior slide. As you can see by the red line, the two lines cross between 8 and 9 units, so the break-even point is somewhere between 8 and 9 units. While we will generally perform break-even analysis using equations rather than charts, the logic is the same. We are finding the point where the cost and revenue lines cross each other. In other words, we are finding the point where revenue equals cost. The equation for the break-even point is one of those rare formulas where it is very easy to see how it was derived, so we will go through the steps. To begin with, we want revenue to equal cost at the same volume X, and we wish to find the volume X. The revenue at volume X is just the per unit revenue R times X. The cost at volume X is the fixed cost, FC, plus the variable cost, VC, times X. The second equation shows this. At this point, I should briefly mention that different textbooks sometimes use different letters for the variables, but the logic is the same. Now for some algebra. First, we will subtract the variable cost at X from both sides of the equation to move it to the left side. Next, we will combine terms on the left side. Finally, we will divide both sides by R minus VC, and that gives us the equation for the break-even point. The break-even point is the fixed cost divided by the difference between the revenue per unit and the variable cost per unit. Plugging in $1,000 for the fixed cost, $140 for the revenue per unit, and $25 for the variable cost per unit, and performing the math gives us a break-even point of 8.70, which is exactly what the chart showed us earlier. In this next example, fixed costs are $5,000, variable cost is $3 per unit, and revenue is $7 per unit. Find the break-even point. Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made. Plugging in $5,000 for the fixed cost, $7 for the revenue per unit, and $3 for the variable cost per unit, and performing the math gives us a break-even point of $1,250. Now let's look at comparing two production methods using break-even analysis. As before, we will start off graphically and then move to equations. When we are looking at a single product, we are looking for the point where the revenue equals the cost, and we call that the break-even point. When we are comparing two production methods, we are looking for the point where their respective costs are the same, and while we can call that a break-even point, it is more appropriate to call it an indifference point. It is called an indifference point because it is a point where the two production methods have the same cost, so we are indifferent between them. That is, we would not care which of the two we use since they cost the same. For this example, production method A has fixed cost of $2,000 and variable cost of $25 per unit. Production cost B has fixed cost of $10,000 and variable cost of $10 per unit. The graph on the slide shows the two cost curves. The blue line is method A. It starts at fixed cost of $2,000 and has a slope equal to the variable cost of $25. The orange line is method B. It starts at the fixed cost of $10,000 and has a slope equal to the variable cost of $10. The two lines cross somewhere around 525, and so that is the indifference point. Since a lower line represents lower cost, below the indifference point we prefer method A, and above the indifference point we prefer method B. With two production methods, in general, below the indifference point we prefer the method with the lower fixed cost, and above the indifference point we prefer the method with the lower variable cost. The equation for the indifference point is another one of those rare formulas where it is easy to see how it is derived, so we will go through the steps. To begin with, we want total cost for production method A to equal total cost for production method B. Total cost is equal to fixed cost plus variable cost at volume X. We subtract the fixed cost for B from both sides and the variable cost for A from both sides to get the fixed cost all on one side and the variable cost all on the other side. Next, we combine terms so there's only one X for the variable cost. Finally, we divide by the combined variable cost term to find the equation for the indifference point. Plugging in the $2,000 fixed cost and $25 variable cost for method A and the $10,000 fixed cost and $10 variable cost for method B and combining terms gives us negative $8,000 over negative $15. The negative terms cancel out and the indifference point is 533, or about what we figured based on the graph. In this example, production method A has fixed cost of $8,000 and variable cost of $12. Production method B has fixed cost of $12,000 and variable cost of $6. Find the indifference point. Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made. Plugging in the fixed and variable costs for methods A and B gives us an indifference point of 666.67. At a lower volume than 666.67, we would prefer method A since it has the lower fixed cost, and above that point we prefer method B since it has the lower variable cost. Now let us take the last example and add a third production method, method C. Method C has fixed cost of $2,000 and variable cost of $30. It is shown on the graph in gray. Methods A and B did not change, so their indifference point remains 667. That point is marked with an A on the chart. Note that we will be expressing all of these indifference points as whole numbers. We already know how to find the points B and C on the chart. Point B is just a pairwise comparison of production methods C and B, and point C is just a pairwise comparison of production methods A and C. Doing the math as shown before gives us point B as 417 and point C as 333. There is not a quick guide to figure out which method is cheaper where. If you have a chart like the one shown, you can read it from the chart. Otherwise, you must compare cost at points just above and below each point to figure out which is the cheapest. As we can see from the chart, below point C, method C is the cheapest. From point C to point A, method A is the cheapest, and above point A, method B is the cheapest. The process would be the same if you had 4, 5, or even more potential production methods.
If you found that this video helped you with your operations management problem, please consider liking the video and even subscribing to the channel.